Hi, welcome to my race presentation. My name is Zhengyu, a rising senior at Hong Kong University of Science and Technology. This summer, I've been working in the Robotic Exploration Lab on optimization-based control. It's my great honor here to present our work on Primal Augmented Lagrangian solver for model predictive control. For those who are not familiar with the term, Model Predictive Control, or MPC for short, solves a trajectory optimization problem several time steps ahead, but only applies the first control input to the actual system. By doing so, MPC is able to reason the potential constraint violation in the future and react earlier. It does a really great job in controlling complex under-actuated robots like rotors and quadrupeds. MPC solves a discrete optimal control problem repeatedly. In general, the problem can be fit into a quadratic programming form shown on the right. The structure of the problem won't change during the execution, but when the new measurement comes in, the numerical value will be updated, and the new QP is solved again to get the control input for the current time step. Recently, there has been an increasing trend in using augmented Lagrangian to solve QP in MPC because of its great ability to handle general state and input constraints speedily. So why do we care about constraints? Because they are widely used to model the ability of controlled system and the environment. For this obstacle avoidance example, the inequality constraints are imposed and the optimized trajectory won't penetrate into the obstacles. The augmented Lagrangian solves the QP by augmenting a Lagrangian multiplier term to the penalty method. The main optimization step is a direct application of Gauss-Newton method. We have to inverse the Hessian to get a delta update of decision variable. As you can see here, the penalty weight shows up in the Gauss-Newton Hessian. While, due to the nature of penalty method, the penalty weight should be sufficiently large in order to achieve better constraints satisfaction. But increasing the penalty will cause the Hessian increasing AO condition and slow down the convergence. To address the AO conditioning issue, we propose a primordial formulation of the augmented Lagrangian that can greatly mitigate the AO conditioning issue. By introducing two dummy variables y and w for equality and inequality constraints respectively, we optimize both the primal variable and dummy variable simultaneously. Compared to the original augmented Lagrangian method, this Hessian doesn't become AO conditioned as the penalty weight increases, because the weight does not appear in the Hessian matrix. Only the reciprocal shows up at the diagonal entries associated with the dummy variables, naturally serving as a dual regularization. However, good stuff always comes with actual cost. The Gauss-Newton Hessian of primordial augmented Lagrangian is not symmetric, and thus slow to factorize. But after doing the math and massaging the equations, we prove the symmetric formulation on the right is equivalent to the non-symmetric formulation on the left, where the diagonal I mu is a selection matrix selecting the active inequality constraints and zeroing out the rest. We haven't included detailed derivation here. Interested audience can refer to the risk journal. The Hessian matrix now is a quasi-definite matrix and thus can be factorized with a faster factorization routine such as LDL. We compare the proposed method with other state-of-art MPC solvers like OSQP and HPIPM over a trajectory optimization problem of a planar drone. The state dimension of the problem is 6, which consists of position x, y, tilt angle theta, and their velocities. The input dimension is 2, which is the thrust of two motors. The MPC horizon is 5 seconds, and the decision variable is 800 in total. The constraint tolerance is said to be 10 to power minus 3. The benchmark was conducted on a commercially available laptop. The constraint stat tolerance is said to be the same across different solvers, and all solvers solve the same problems till convergence. The absolute solve time is listed in table, and the normalized solve time is shown in the figure. For this specific MPC problem, the proposed method outperforms the OSQP by almost a factor of 2, but is still significantly slower than HPIPM. The Primal dual augmented Lagrangian solver is still under active development, and a lot of possibilities can be explored in the future. Currently, the most expensive step is the matrix factorization of the Newton set, as the cost Hessian and dynamics equality constraint matrix are quite sparse and follow a specific pattern. We are trying to leverage those patterns and speed up the solution. The current prototype is implemented in C++ with Eigen. It's already fast, but we can be faster by using a better linear algebra routine like BLASTFIELD. A rough benchmarking shows the Cholesky factorization of a small size matrix in BLASTFIELD is 5 times faster than that in Eigen. It seems really promising. And that's all of my presentation. Thank you.